Good morning, everyone in Europe, and afternoon or evening to those joining from elsewhere. Welcome to the fourth day of the European Einstein Toolkit meeting. We hope the meeting has been going well for you and that it continues to be useful and enjoyable. We will have two speakers in the morning sessions. The first one is Carlos Palenzuela. Carlos is a professor of physics at the University of the Balearic Islands. His research includes binary-neutron-star, black hole-neutron-star, binary black hole, and binary boson-star mergers. Today we will be hearing BNS and BHNS mergers with MHDuet by him. Carlos, you can continue from that. Thank you.
Good morning. Thank you very much for the introduction, and thank you for inviting me to give this talk that is going to be about compact binary mergers made with MHDuet, and I will try to emphasize what makes these simulations different from other simulations that have been done by different groups, and also what made our code a little bit different from the other ones that have been introduced here in this meeting. So, well, I will first I give a short introduction on what is the problem. Then I will focus on what makes our simulations a little bit different from other ones. That is basically we are using Large-Eddy-Simulation techniques with some subgrid scale models, specific subgrid scale models. Then I will talk a little bit about our numerical code that we use to perform this simulation, that is MHDuet, that is different from the Einstein Toolkit. It is a code that we develop. And then finally, I will summarize some of these Large-Eddy simulations of binary neutron stars and binary black hole neutron stars. Well, first, it is probably not necessary that I stress how important is the role of the magnetic fields in binary neutron stars mergers, or binary black hole neutron star mergers. The imprints of the large-scale magnetic field, well, can induce some effective viscosity in the remnant that will enhance the transport of angular momentum and also the thermal pressure. So it will probably, or it actually, it produces a larger secular ejecta that is going to be seen later in the thermal radiation as a kilonova. So it's going to change the spectra of the kilonova, or it may change the spectra of the kilonova. And of course, the magnetic fields will form, or we expect them to form, some sort of helical structure near the rotation axis that is going to produce like a jet, a magnetically illuminated jet, that is going to be the precursor of the short GRBs. So it can have an impact on the two observables, the electromagnetic observables, from that we expect, or that we have seen already in these mergers, in these events. And so it is important to understand how is the evolution of the magnetic fields in this scenario, because we know that the stars, the neutron stars, have magnetic fields, but they are small, too small to produce any significant impact in the dynamics after the merger. So if there is some impact, so these magnetic fields have to be amplified somehow. And the process that from the theoretical point of view and numerical simulations have confirmed in which this amplification takes place is that at the time of the merger, we have like two balls of fluids that are moving in different opposite directions. And so the interface between two fluids is going to be prone to the Kelvin-Helmholtz instability. That is going to produce eddies at different scales and smaller scales. And the interaction of these eddies the nonlinear interaction of these eddies is going to produce a turbulent regime, a turbulent state. And the magnetic field is going to be stretched and twisted with these eddies, and then it's going to be amplified in what is called a turbulent dynamo that is happening in very small scales. So it's mostly happening in small scales and in very short times. And here we have some snapshots of how the Kelvin-Helmholtz instability starts to act during the merger, amplifying the magnetic field that is here in red and blue. After some time, most of the star is in this turbulent state. That we can see the small scale, almost random magnetic field, but with a very strong magnetic field, a very strong magnitude. And then we expect that at later times, some processes associated with the rotation will convert this small scale magnetic field into a large scale magnetic field that can produce the magnetically dominated jet that we observe in the short GRP. So if we make a diagram of the energetics and put the large scales on the top and the small scales at the bottom, we see that during the merger, part of the gravitational energies gets converted into kinetic energy at large scales during the in spiral. And at the time of the merger, the small eddies, the Kelvin-Helmholtz instability, basically transfer energy from large scale to small scales, to eddies that are smaller and smaller through the Kelvin-Helmholtz instability. This is the standard direct kinetic cascade. And then the stretching of the magnetic fields in these eddies that happens at all the scales, but mostly at the smaller scales, it's more efficient at smaller scales, is going to convert kinetic energy into magnetic energy. So it's going to be some sort of dynamo. And then we expect that, as I said, some processes associated with the rotation will transfer back from the smaller scales to larger scales the magnetic field, and then to produce the magnetically dominated jet that we observe as a short GRP. So this is in theory, and this is what should happen in the continuum. The problem is that when we try to model it in our numerical simulations, basically we have some cutoff scale that is given by the resolution of our simulation. And so we cannot capture or we cannot model what is happening below this resolution that is given by our computational resources, by our the grid spacing of our mesh. So basically, we can resolve the large scales, where there is some transfer from kinetic to magnetic energy, but we cannot resolve the smaller scales where most of this transfer actually happens. So we cannot really capture all the dynamo that is, or the turbulent dynamo that is happening at the smaller scales. So what do we do in those cases, or what is the effect? Well, one can always try to push this bar lower and lower by increasing the resolution, but even with the highest resolutions, it has not been observed a convergence of the magnetic field at the saturation, when this turbulent state saturates, even with resolutions of 12 meters. So people, in order to balance this lack of resolution, what they use is to start with a large scale initial magnetic field to compensate for the turbulent dynamo that we cannot capture during the merger, with the hope that later we will be able to capture the dynamical processes associated with the rotation that are proportional to the magnitude of the magnetic field. The problem is that when we do that, we may be missing some physics or something, and because we know that this choice is unrealistic. We know that from observations that magnetic fields in neutron stars larger than 10 to the 11 are unrealistic. So the question that I'm going to try to answer in this talk is, what is the topology and the intensity of the magnetic field after the merger? And we are in a situation where we have to choose between two bad choices. So we have to choose the lesser of two evils. Either we impose an unrealistic large initial magnetic field to compensate for this turbulent dynamo that we cannot capture, or we have to do some extra work and to improve our solutions in different ways. Either we improve numerical methods with higher order schemes, or we improve the resolution, and then we have to go to exact scale infrastructures with more efficient AMR, with GPUs, possibly. Or we can try to improve the modeling of our solution. And this is what I am going to discuss here with the Large-Eddy-Simulation techniques. Then I will show some the latest results in the magnetic field dynamics in bit binaries, neutron star, and black hole neutron star. And I will describe briefly our computational code that is MHDuet. Let me start with the Large-Eddy simulations and with the diagram that I draw before about the large scale, the small scales, and this cutoff scale that is given by the resolution of our simulation. And this is something that happens in binary neutron-star mergers, but also in many other MHD problems. It happens in the sun, it happens in many engineering problems. And what they do there is, well, there are different approaches. The direct numerical simulation is where you try to resolve all the scales, but we have seen that that is unachievable in our case. The next approach, or simplest approach, is to do these Large-Eddy simulation techniques where you evolve or you solve the large scales and you model somehow the smaller scales. You model the effect of the smaller scales in the large scales in your evolution. And you can do it at the continuum level with some filtering size that we are going to associate with the finite discretization resolution of our mesh, of our grid. So basically, you split the solution into a smooth filtered quantity, F bar, and an unresolved residual, F prime. And in order to get the F bar, basically you multiply by a kernel the solution, the full solution, and integrate a kernel of compact support, and integrate in all the domain, in the volume. No? And you can see here an example that if you use some sort of Gaussian kernel, the solution that have very short wavelengths, basically it is smoothed out, it is averaged in something that it looks more amenable for numerical simulations. No? So the choice of the kernel is important. The simple box kernel is just like a box, like a hat, and that is basically what we do when we perform numerical simulations in finite volume. We are like averaging in a cell our quantities. So this could be the equivalent of what we do in finite volume. But for the calculations that I will describe later, it's more convenient, a smooth Gaussian kernel that we can make it almost to match up to the second moment the box one if we with this choice of the width, with A is equal to the delta squared over 24. No? And just to notice that this filtering operator, it commutes both with the special and the time derivative, so it's very easy to compute what is the evolution equation for the filtered part of the solution. No? So if we apply to the simple Burgers equation, that is a nonlinear equation, well, at the continuum problem, we know what is the evolution equation, that is this one here. We apply the filter by multiplying by the kernel and integrating in delta x prime, and then we get this discretized or filtered problem. But this problem is not closed because we don't know how to calculate U square, the average of U square. We know how to calculate U bar or U average, but not U square average. So we are going to hide our ignorance by adding and subtracting what we know. So to recover the original equation, and plus some subfiltered scale tensor, that is basically this commutation of the nonlinear operation that are in the fluxes with the average operator. No? And this is basically what we all do when we solve a problem with finite volumes. Even without knowing or without realizing, we are using some Large-Eddy simulation techniques where we are setting or using the lowest order approach where we are setting this tensor to 0. No? But we are all doing it without even realizing. How can we go farther than the lowest order approximation? Well, there are several ways. The nicest one that I found that it doesn't depend on doesn't make any physical assumption is this gradient subgrid scale model that is based basically that in the fact that the convolution in a space domain, that is basically this filtering operation, is just a product in Fourier domain. So the inverse of the Fourier transform of this product in the Fourier space is basically the average of the filtering operation. We can also use that with the smooth Gaussian kernel in Fourier space have the same form, and that we can also expand it in Taylor series. And in this Taylor series, well, in Fourier space, it's just a derivative of order n in the standard space. So using these three components, that the convolution in space is a product in Fourier domain, that the Gaussian kernel is the same in Fourier or in the standard space, and that this expansion, the derivatives are just powers of k in Fourier, we can develop in series with different terms, and we get at the lowest order, the average of a product is just the product of the averages, plus at the next order there is a term that is the gradient of the averages, or the scalar product of the gradient of the averages. And this is why it is called gradient model. So basically, this means that what we have been doing until now when you do finite volumes is just to assume that this average of a product is the product of the averages. But if you want to go a little bit further and see what is the effect of these small scales that we are missing in your system, you can actually add the next leading order term. Of course, this term is going to depend on what is the form of your equations. So for instance, for the Burger's equation that I described before, it is, well, the zero order cancel, and then the first order is just the gradient of the u square, where remember that this a is proportional to the delta square, so that means that this term is going to vanish at the continuum limit. So we have consistency, and that guarantees the numerical convergence to the continuum solution. And also that this term is highly nonlinear. So if it was just a dissipative term, it could be just a first derivative, but this is a first derivative square. So it has not a defined sign, so it can account for energy transfers in both directions. So it's not just a simple diffusive term. Well, we can generalize it, this gradient model for different equations, for a general balanced law form, or for a system of equations in balanced law form. We can filter, rewrite the equations, and so that you have this subfilter scale tensor is just the flux of the average minus the average of the flux. And we can use this simple recipe to write down what are the new terms. And for Newtonian MHD, we did it in a work with Daniel Vigano and other people. And these are the equations, the filtered equations. These are the unknown subfilter scale tensors. And then using the gradient models, these are the terms that basically go here, in this tau, the subfilter scale tensor. We can also generalize it to GR. In GR, it's a little bit more complicated because the recovery of the primitives from the conserves is nonlinear and it cannot be written in an explicit way. But with some mathematics, it can be done. It was done by Federico Carrasco in our group. And it is much longer than in Newtonian MHD because of all these couplings with the Lorentz factor, but it still can be written in 2 slides. So it's more complicated than a standard fluid, but much less complicated than Einstein equations, for instance. We can also assess if this approach is correct, and for that we can take just some simulation with high resolution, and we will consider that this high resolution is the full solution. Then we can take averages of this solution, like with some compact support kernel, and we can also construct with this the residual by subtracting these two. And with all that information, we can basically compute the subfilter scale tensor given by the definition, and also given by the subgrid scale gradient model. No? And if they are correlated by some proportionality constant, means that the model is okay. If not, it means it is not correct. No? And how good the correlation is given by this Pearson correlation coefficient, and the proportionality factor should be close to 1. So we did some simulations with the Kelvin-Helmholtz instability, and at different times with different initial data, with different filter sizes, and basically we obtained that the Pearson correlation with the subgrid scale model is actually very good. It's close to 1, and that the proportionality constant is also close to 1. So the model seems to be doing what it is supposed to do. It is including the effect of the small scales in the evolution of the large scales. No? We also compare with different subgrid scale models, with the dissipative one, with the cross-helicity, and for the only one that we got like a good correlation, actually, in all the cases that we consider, was with the gradient subgrid scale model. So not every model is going to work as we expect, no? At least not in all the situations. And this is the nice thing of this gradient model, that doesn't make any physical assumption, and it is just going an order higher than what we usually do in finite volume, no? When we resolve equations with finite volume. Well, now let me describe briefly the code that we have used for the simulations. It's called MHDuet. It's a high-order general relativistic radiation MHD code for CPU and GPU architectures. The paper appeared recently on the archive and also in CQG. You can download the code that is publicly available with some instructions from this web page that was developed by Steve Liebling. And this code actually is not new. It has been there already for 7 years. In the first paper, this Simflowny-based finite difference code, we didn't give it a name. And neither in the next paper, where we made a comparison with some older codes. But well, since 2 or 3 years ago, it is being called, we give it a name so that people can recognize it. No? But it has been there around already for 7 years. First, the equations of motion that we solve with this code are the standard, are the Einstein equations for the gravity with the CC set4 formulation that very close or very similar to the BSSN, if you are familiar with any of those. We also solve the GRMHD equation with divergence cleaning, and also with these Large-Eddy-Simulation techniques with the gradient model that are these G terms that are here in the equations. We also have N1 neutrino transport with fully coupled neutrino fluid in the sources, but I will not discuss this because we don't have enough time. And an important thing is that it uses high order numerical schemes. So we are using a fourth order, fourth and second, an Imec-Grun-Hekuta, that is fourth order for the explicit part, and second order for the neutrinos that are implicit part. We also use fourth order finite difference special operators for the Einstein equations and the subgrid scale tensors with sixth order Kreiser-Lueger dissipation, and with a fifth order high resolution shock capturing methods, which are based on finite difference. No? That means that although the discretization of the flux is performed in a conservative way, as in finite volume, these fluxes at the interfaces are computed based on a reconstruction of points at the grid points, no? Following just the LLF flux splitting that was described in the paper of Xu in '98, where we used the MP5 reconstruction because we realized that it was very robust and very faster than others. For the optimization strategies, we are we are only allowing for vertex or node-centered discretizations. That makes the AMR interfaces much simpler. And in particular, the prolongation procedure, when we have to create new refinement grid points, can be performed just with this very easy and fast interpolation. Right now, we don't have any refluxing, so there is no strict conservation of the organic number, at least not beyond the discretization error. And we are using a subcycling in time through the Berger-Oerlinger without order reduction that was also introduced in a paper of McQuartle and Colella in 2011 that basically allows you to achieve high order accuracy in time with a stencil that is only order 2. No? So that also is it's not only high order, but it's also very efficient when you parallelize and you have to transfer data from one processor to another. What makes the code a little bit different from others is that the code is actually generated automatically by another platform that is called Simflowny that we developed here, where you can see that this is the standard, well, the platform works like in a web format or interface where you put your parameters, put your evolution equations, select some numerical methods, push a button, and then it creates some code, some template code that can be compiled with the SAMRAI libraries or with the AMReX libraries. But the original code is in Simflowny, it's exactly the same. So but you can create code for either SAMRAI or AMReX infrastructure. No? The code is also publicly available. You can check it here if you're interested, where there are already many models, problems that you can test and play with. So with this Simflowny platform, we generated the same code or the code solving the GRMHD equations in SAMRAI and in AMReX. And the first test that we did is, well, not the first, but one of the tests that we did is to solve a non-rotating neutron stars with a realistic equation of state, a microphysical equation of state, where we know what are the quasi-normal modes. No? The first thing that you can see here in the top, I am showing the density as a function of time at the center of the star. And it's that although the codes are different because they run on different infrastructures, they give exactly the same results at 2-machine precision. So the SAMRAI code and the AMReX code, although they are different in principle because they use different infrastructure, different fields, different variables, different way of parallelizing and doing the AMR, they give the same results. And I think that is quite nice. And the second thing is that as you go to higher resolution, well, you get closer, or the quasi-normal modes get closer to the ones already given in the literature. No? So it seems that we are approaching to the correct solution. We also did some rotating hot magnetized neutron stars, where you can see the density at the center, the magnetic field, that is actually quite high, 10 to the 16, the temperature, and here the convergence order. And so the different quantities converge at least to second order or higher. And we did also some benchmarking for this test, where we compare the time that takes for cells and cycles, that is a standard quantity, as a number of nodes, either CPU or GPU nodes. No? A CPU node have like 112 cores. A GPU node have like 4 GPUs. No? Here at the top, you can see the result of this benchmarking with CPUs. When we go, all these curves at the bottom are done with GPUs. And you see that going from CPU to GPU, at least comparing node to node, give you more than a factor 10, no, in a speed up. In particular, if we compare in Mare Nostrum, we get almost a factor 15 or 20. And here I plotted 2 curves. One, it doesn't have subcycling, and the other with subcycling. So this, adding the subcycling in our scheme, basically, at least with GPUs, gains a factor of 2 in a speed up. No? We also did some binaries, binary neutron-star with DD2. Here we just see 3 snapshots of the density and the temperature. And we also computed the waveforms for different resolutions, the frequency, the instantaneous frequency of these waveforms, the dephasing, and the convergence of the dephasing was again higher than 2. So we can say that it is converging to high order, at least up to the merger. And with this code, we applied or we performed some binary neutron stars and binary black hole simulations using these less techniques that have been, the results have been published in different papers. No? Well, first we start with either of these binaries, or one of these binaries in quasi-circular orbits, where we don't start with a strong magnetic field, but we start with something that is more realistic, with 10 to the 11 Gauss, which are confined inside the star. Here we were using the hybrid EOS with the conversion from to primitive via the reprimand developed by Castañ. And here we were only using the subgrid scale model for the induction equation with a factor that is larger than the analytical prediction, that should be 1, to compensate basically for numerical dissipation. Basically, we still have too much numerical dissipation in our simulations, and in order to compensate for that, we need to increase this factor. No? And we did some high resolution simulations with resolutions in the case of the binary neutron star that went to 30 meters, and for the black hole neutron star up to 90 meters, in covering most of the remnant, no? The bulk of the remnant. Here you can see the magnetic field in the equatorial plane at different times of the mergers for different cases where we were changing the topology of the initial magnetic field. So this is the standard case or our fiducial case where the magnetic field was 10 to the 11 Gauss in average, and it was dipolar, large scale, and aligned with the angular momentum of the system. In the second one, we have it's also dipolar and aligned, but it is much stronger, 10 to the 14 Gauss. In the third one is dipolar, but it's perpendicular. It's directing perpendicular to the angular momentum. And in the last one is multipolar. And you can see that although the magnetic fields are very different at the beginning, as time progresses, the magnetic field strength looks quite similar, actually almost indistinguishable. We also tried with different binary parameters, changing the total mass, changing the mass ratio, adding a spin to some of the stars with some periods. If it is infinite, it means it is not rotating, but here it is rotating with different equations of state also. And in most of the cases, we see basically the same, that at the beginning is very different, but as time progresses, the magnetic field looks more and more similar. So this summarizes a little bit the results, where we show the average magnetic field in the bulk and in the envelope. And the first thing that we can see here in red is that in the simulation without less, that are the dashes, as we increase the resolution by a factor of 2, we get a very different value of the magnetic field at the saturation level, as Shibata, Kiuchi, and other people already found. But when we use the less, the medium and the high resolution already gave the same results. So we found some sort of convergence on the saturation level of the magnetic field for the very first time. No? So it seems that the less techniques are actually capturing some of the smaller scale effects of the simulations. And then another observation, just comparing the magnetic field average as a function of time for the different cases, is that we obtain comparable magnetic fields independently on the initial magnetic field that we set it, the topology or the magnitude, and also independently on the binary parameters. No? So the very short summary would be that the magnetic fields are amplified from 10 to the 11 to 10 to the 16 Gauss in average in less than 5 milliseconds after the merger, and that this final magnetic field that it's obtained at this time is isotropic, turbulent, that have no memory from the initial state, and where we find the equipartition between the toroidal and the poloidal components. No? So there is some sort of universality of the magnetic fields in BNS remnants, because the turbulent state that is produced by this Kelvin-Helmholtz instability basically erases any memory from the initial magnetic field and produces a turbulent isotropic one with a very strong magnitude. And this is something that happens for any small magnetic field that you set, or for any binary parameter.
Carlos, you have 5 minutes before the questions. Yeah.
That's more than enough. Thank you. Well, we also did some binary black hole neutron star simulations. Here are the density in the equatorial plane at different times, where you can see that the neutron star is disrupted outside the ISCO. Part of the star starts to fall into the black hole, leaving like a tail. At some point after a period, or a little bit more than a period, the tail after the disruption, the head of the tail will hit the back of the tail, and there will be some turbulence, some Kelvin-Helmholtz instability, and the tail or the tidal, the matter that is left forms, basically it circularizes and forms a disk, an accretion disk around the black hole. If we look at the magnetic field magnitude, we see something similar, weaker, but similar to what we observe in binary neutron stars, but now extended in the remnant, that is the disk, where we see that the magnetic field is small initially, but as this turbulent state goes on, the magnetic field gets amplified until reaching values of 10 to the 14 Gauss. No? We explore different cases or different spins of the black hole that leads to different masses of the disk that range from 10 to the minus 3 to 5 times 10 to the minus 2. And here is the density, poloidal component of the magnetic field, the toroidal component. You can see that it's very turbulent, again, a small scale. And first thing is that we didn't find a convergence as good as in binary neutron stars, but still it was converging to a convergence factor order higher than 1, and the final number that we could extrapolate it was very similar to the result of our high resolution. And what we also observe is that the magnetic field, although it is different for the different cases, it has a very mild dependence. So the average magnetic field is always around 10 to the 14 Gauss. So the final summary is that, well, both simulations behave similarly, because in both simulations there are some turbulent state that in neutron star produces or leads to magnetic fields in average of 10 to the 16 Gauss in less than 5 milliseconds, with minor dependence on the parameters. Also in the black hole neutron stars, final state of 10 to the 14 Gauss in less than 20 milliseconds, again with a mild dependence on the disk mass. And in both cases, the magnetic field is isotropic and turbulent, so there is some universality of the amplified magnetic fields in both scenarios. And I finish with this, that if we have to choose between these two evils, well, then choose both of them. No? Instead of, if you have to impose a realistic large initial magnetic field to compensate for this turbulent dynamo, well, do it in a way that is consistent with the physics, no? That is isotropic and a small scale as the one that is resulting from the turbulence regime. And also, if possible, try to use, well, high order schemes, high resolution, and less techniques in order to take into account the small scale dynamics. And here at the bottom, I'm just showing 3 simulations. The right one, or the most correct one, is the one at the right, which had the less techniques and higher high resolution. And if you compare with two simulations with low resolution without the less, and one it has a topoloidal magnetic field and the other is a small scale isotropic turbulent magnetic field, you see that the one that is closest is the one with the isotropic magnetic field, even if it is strong. And with that, I will stop. Thank you very much for your attention.
Thank you very much, Carlos, for a very nice talk. And we will now have questions.